So if we were to write up the results from that t-test um, in APA format, it would look something like this. The mean score for condition D, then you report the mean for that, which is 60, was not significantly higher than the mean score for condition C, which was 50. Then you report the statistics. T, telling the reader that's a t-test. The 8 degrees of freedom tells the reader that there were 10 participants total, equals negative 1.58. P is equal to 0.15. The negative 1.58 is your t statistic. That is then gives you a p-value of 1.5. That's the probability of getting that t statistic if the null is true. So there's a 15% chance of getting a t-value of 1.58 if the null is true. That probability is greater than our cutoff for alpha, which is 0.05. Therefore, we fail to reject the null hypothesis. Let's try another example. So this is now conditions A and B. Both conditions have 5 participants. The mean for A is 50. The mean for B is 60. They both have standard deviations of 1. Because our Levene's test is not significant, we can now use the equal variance assumed in that second box here, which gives us a t-value of negative 15.811. Again, 8 degrees of freedom because we had 10 participants. And then our p-value is so small that it can't even be written here. It's 0.000. So it's less than, obviously, our cutoff of 0.01 or 0.05. So that would be statistically significant. If we were to write it up, something like this would be one way you can write it up. The mean score for condition B, M of 60, was significantly higher than the mean score for condition A, mean of 50. Our t statistic, we have 8 degrees of freedom. The t-value is negative 15.81. The p-value is less than 0.001. And because that 0.001 is less than either alpha 0.05 or 0.01, we can conclude that we have a statistically significant difference between our two means. Now remember, the key here is for the example when we looked at C and D versus A and B, is that A and B, the means were the same for both examples, but the variability around those means were much smaller for A and B versus C and D. And that's why A and B were significant. That difference was significant, but the difference between C and D was not. Finally, let's talk about different types of t-tests and when to use these different types. So the most common type of t-test that you would run would be called an independent samples t-test. And that's what we ran for these past two examples. Those were both independent samples t-tests. Now, independent samples t-test, as the name implies, means you have independent samples. That means the people in one condition were different than the people in the other condition, right? So you have two groups, one independent variable with two groups. The dependent variable is normally distributed, and that's true for all the different types of t-tests. One of the basic assumptions for a t-test, and when we get to ANOVAs and ANOVAs as well, is that you have normal distribution of scores. And then finally, because the groups have to be different, this is the type of t-test that you would use if you had an independent groups design. Remember, independent groups design means that you have two independent samples of participants. So you would use an independent samples t-test to test that type of a t-test design. So an example here would be if you randomly assign people to either drink coffee or to drink, water as a control group, and then you measure their attention on a 100-point scale, right? The dependent variable would be their scores on that attention scale, and the idea being that people are only assigned to drink the coffee or drink the water. Another type of t-test is what's called a paired sample t-test. And this is when you have, again, one independent variable with two levels, and the dependent variables will be distributed. But now participants are going to be assigned to both levels of the independent variable. So this is what you would use if you had repeated measures design, or also what's called a within groups design. You would run a paired sample t-test. So an example here would be here, you give participants a cup of water, measure their attention, and then give them a cup of coffee and measure their attention again. So as you can see, participants are both levels of the independent variable. They get the control condition, then they get the experimental condition. Then the last type is what's called a one sample t-test. This is when you have only one group of participants and they're compared to a known population parameter. So the example that we had before when we had people we had them take a test and compare their scores to an IQ test for the general population of 100, that general population of 100 would be that known population parameter. So we're comparing the scores of our group to the scores for what we know to be the mean for the population, which is 100. And again, for all these examples for a t-test, the dependent variable is normally distributed. So again, our example here is you give people an IQ test and you compare their scores on that IQ test to the known population, which is 100. So in summary, the t-test is a very useful tool when you're looking at just two groups and you're trying to look at differences between the means and also variability around those means. So you have between group variability, which is the difference between the means, and within group variability, which are how far the scores are from those means. The larger and you create a ratio for that. The larger that ratio, the more likely it is that you're going to have a statistically significant result. T-tests can definitely be used when you're looking at either directional or non-directional hypotheses. So a directional hypothesis would be considered a one-tailed hypothesis. A non-directional hypothesis would be called a two-tailed hypothesis, where you're not really sure exactly which one's going to be different than which one's going to be higher, but you're arguing that they're going to be different from each other. And t-tests can be used to compare two independent groups, two paired groups, or one group in comparison to a known parameter.